Let us recall the hanging question we posed earlier. Why are we able to hear the voice of a person even if he is not within sight? We can hear a person without seeing him because sound waves can be diffracted. It can bend around corners. What does this mean? Let us watch water waves in a ripple tank as they pass through a barrier. Again, we have Leah here to assist us in our demonstration. We have the ripple tank and these are the two barriers. Take note of the waves which pass through the edges of the barrier and those which pass through the opening. Observe what happens when we make the opening smaller and smaller. Do you see the waves spreading out? We notice that the incident straight wavefronts emerge as straight wavefronts from a wide opening, but they become curved after passing through a narrow opening. And as we make the openings smaller, the emergent wavefronts become more curved until finally, when the size of the opening is less than or equal to the wavelength, the wavefronts become circular. This means that whereas before, the straight waves are just moving in one direction after passing through a narrow opening, the wavefronts are moving in different directions. The waves spread out. They diffract after passing through an opening of size compatible to the wavelength. This spreading out or diffraction is also observable when waves meet an obstacle about the size of the wavelength. You will learn more about diffraction of sound in a succeeding episode. We have seen the interaction between waves and physical barriers. What happens when a wave meets another wave? First, let us observe spring waves. We have our spring here. I'll operate it from this end, and we have Leah on the other end. Hi, Leah. Hi. We shall generate pulses at the two ends of the spring. Focus your attention at the point on the spring where the pulses meet. Let us have two pulses with displacements in the same direction. Okay, watch. At the point where the pulses meet, the displacement of the resultant pulse is greater than those of the individual pulses. In fact, the amplitude of the resultant pulse is the sum of the amplitudes of the individual pulses. We also notice that after meeting, the individual pulses went their own way as if nothing happened. Now, let us have two pulses with opposite displacements. What happens at the meeting point? At the point where the pulses meet, the displacement of the resultant pulse is less than that of the individual pulses. What we have demonstrated is the principle of superposition, which states that the resultant displacement at any point in a medium, at any instant, may be found by adding the instantaneous displacements that would be produced at the point by the individual waves if each were present alone. Let us use the ripple tank again, and here you can see 2 point sources connected to a single vibrating source. These two sources move with the same frequency and are always in phase. Such sources are said to be coherent. Each point source generates circular ripples. The ripples from the two sources meet, and here is a pattern formed when waves from the two sources meet. Okay? So note the regions of alternating dark and bright band, labeled A, for the antinodes, and the gray regions, labeled N, for the nodes, where the water seems to be still. This pattern is what we refer to as an interference pattern. In the region of alternating dark and bright bands, there is constructive interference. In constructive interference, the crest of a wave from one source meets the crest of a wave from the other, forming a crest twice the amplitude of either one of them, and the result is a bright band. So for instance here, consider this line AO. Here, crest meets crest, and here, trough meets trough, and so on. So this is where constructive interference is observed. Similarly, the dark bands result when troughs from the two sources meet, as what we have explained. Now, the gray region is an area of destructive interference. Here, the crest of one wave meets the trough of another and results in zero amplitude or zero displacement. For example, gray areas are represented by these regions here. So for instance here, crest meets trough, and so on, giving us areas where we have destructive interference. How does interference pattern change with the change in wavelength? Watch carefully. Remember, interference of waves can be observed only when the sources are coherent. Interference results when waves superimpose. So we explain interference using the superposition principle. We shall wrap up today's lesson after this short break. Stay tuned. When we observe simple occurrences that happen in everyday life, do we actually experience the phenomena we have described in this lesson? Yes, we do. Next time you go to the beach, look for reflected waves when they hit the shore. Watch the waves bend when they travel from the deep end towards a shallow portion. Observe the waves as they go around obstacles, and watch out when two waves meet. Their amplitude may be so high that the energy they carry would be enough to topple you down. We will again be encountering and referring to these properties of waves when we study light and sound in the succeeding episodes. For now, let's summarize the important ideas we have learned today. Reflected waves are those which bounce back after hitting a barrier. The incident and the reflected waves travel in the same medium. In reflection, the angle of incidence is equal to the angle of reflection. Refraction is the bending of waves as they cross the boundary between two media. Refraction is due to the change in the velocity of the waves as it travels from one medium to another. Diffraction is the spreading out of the waves as they go around obstacles or through openings. Diffraction of waves can be observed only when the size of the obstacle or the opening is comparable to the wavelength of the waves. Interference occurs when two waves meet. In constructive interference, a crest meets a crest, or a trough meets a trough, resulting in waves of maximum displacement. In destructive interference, a crest meets a trough, resulting in zero displacement. Interference is explained by the law of superposition, which states that the displacement at any point at any instant is the sum of the instantaneous displacement of the individual waves if present alone. Well, That's all we have for today, dear teachers. Thank you so much for joining us today and every week for an exciting episode or encounter with the world of physics in everyday life. This is your fellow physics teacher, Zenny Domingo. Hanggang sa muli!